The world's oceans contain at least small amounts of most of the chemical elements. Here are some of the various chemical species that occur in seawater, shown with their relative molecular concentrations. In recent times, chemists have attempted to extract some of these elements for man's benefit, in much the same way as valuable ores are mined on land. One of the chemicals that is needed in ever-increasing quantities is elemental bromine, yet it occurs in seawater in the form of bromide ions in only very minute concentration, 15 ions per million molecules of water. How can the element bromine be extracted economically from seawater? To answer this question, we must first explore some of the properties and chemistry of bromine. Here is a sample of the element. Bromine is the only non-metallic element that is a liquid at room temperature and pressure. Because of its high vapor pressure, bromine evaporates readily even at room temperature, forming a colored gas. Bromine is highly irritating and toxic. Special precautions must be taken in handling it, including rubber gloves and an exhaust system. Note that the gas is more dense than air. How does bromine react with some common elements? First, let's try the non-metallic element phosphorus. A reaction takes place. The product is phosphorus tribromide, which fumes at the reaction temperature. Now let's see how bromine reacts with the element hydrogen. We pour out a sample of bromine. Since we will be dealing with gaseous, not liquid bromine in this experiment, we can dispense with the gloves. A large beaker is heated so that when bromine is poured into it, the liquid vaporizes and fills the beaker with gaseous bromine. Let's turn on the hydrogen and light it. In the air, the pale blue flame of burning hydrogen is hard to see. But look what happens here. The flame continues to burn in the bromine vapor. Hydrogen reacts with bromine, forming hydrogen bromide. Now, to another sample of bromine, let's add aluminum. Not much happens at first. But once the oxide coating on the aluminum is penetrated, a vigorous reaction takes place. Similar experiments would show that bromine reacts with most of the other elements. Here, the aluminum and bromine combine to form aluminum bromide, which, when purified, gives this solid. Is this bromine compound soluble in water? When water is added, a vigorous reaction occurs as the aluminum bromide dissolves. Here's the purified product from the phosphorus and bromine reaction. Phosphorus tribromide is a liquid. Again, we'll add water. The reaction starts slowly, but soon gives off so much heat that bubbles of steam are formed. The reaction continues until all the phosphorus tribromide has dissolved. This bottle contains pure hydrogen bromide, the product of the earlier reaction between hydrogen and bromine. When we let hydrogen bromide come in contact with water, we see that the water level rises rapidly, indicating that hydrogen bromide too is very soluble in water. Because bromine reacts readily with many substances, and because the resulting compounds are highly soluble in water, Virtually all of the world's bromine compounds are dissolved in the oceans or are trapped in underground brine deposits. But what about the solubility of bromine itself? When bromine is added to water, it settles to the bottom, indicating it is more dense than the water. Now we'll mix the bromine and water with the help of a magnetic stirrer and a plastic-coated magnetic stirring bar. Vigorous and prolonged stirring gives us a saturated solution. The brown color is characteristic of aqueous bromine solutions. However, some drops of bromine remain undissolved. This indicates that elemental bromine is not highly soluble in water. What are some of the chemical properties of this aqueous solution? Let's divide the saturated solution in order to check the effect of varying the acidity. To this flask, we add acid. The color does not change appreciably. A base is added to the other flask. The bromine solution turns a very pale yellow, indicating that a reaction has taken place. Analysis shows that addition of hydroxide ions forms bromide and hypobromite ions. Is the reaction reversed when acid is now added? Yes. As the concentration of hydroxide ions is lowered, the bromine color intensifies. Thus we see that bromine can exist in aqueous solution in various forms which are in rapid, reversible equilibrium. Now let's try to obtain elemental bromine from seawater, making use of our knowledge of the properties and chemistry of bromine. When seawater is first concentrated by a factor of about 50, it will make color changes more visible. The absence of any brown color indicates that no great amount of elemental bromine is present. When we check the acidity, the litmus turns blue. Seawater is basic. Since seawater contains hydroxide ions and also bromide ions, perhaps the equilibrium we studied earlier exists. If so, by adding acid to lower the hydroxide concentration, we should be able to produce elemental bromine. Let's find out. When acid is added to our sample, there is no color change. Therefore, no visible amount of bromine has been produced, even though the solution is acidic, as indicated by the litmus. Apparently, the hypobromite equilibrium is not significant in seawater. What is needed to change the bromide ions to elemental bromine? From the formulas, we see that 2 bromide ions can form a bromine molecule by losing 2 electrons. That is, the bromide ions must undergo oxidation. To find an oxidizing agent, we refer to a set of E0 values. The value for the oxidation of bromine is minus 1.06 volts. We note that the E0 value of oxygen is minus 1.23 volts, which makes it a better oxidizing agent than bromine. Furthermore, oxygen is the cheapest oxidizing agent. Let's find the E0 value for the overall reaction. The E0 value for the oxidation to give bromine is minus 1.06 volts. The E0 value for the oxidation to give oxygen is minus 1.23 volts. We transposed the lower equation to obtain the E0 value for oxygen acting as an oxidizing agent. It is plus 1.23 volts. For the sum of these half reactions, E0 is plus 0.17 volts. The positive value indicates the reaction should occur, but tells us nothing about how fast equilibrium will be reached. To test our prediction that bromine should be formed, let's bubble pure oxygen through the solution and see if the reaction will proceed. There is no immediately visible effect. Apparently, the rate of reaction is too slow to produce any visible amounts of bromine. So we again check our table for another cheap but hopefully faster agent to oxidize the bromide ions. Here is chlorine. It is relatively inexpensive. As before, we calculate the E0 value of the overall reaction. The net reaction has an E0 value of plus 0.30 volts. Although this does not indicate the rate of reaction, it tells us that the oxidation of bromide by chlorine should proceed. We can check this reasoning by experiment. We'll add chlorine to concentrated seawater in an attempt to produce bromine. It works. The color gets deeper and deeper as more and more bromine is produced. The addition of chlorine has resulted in an aqueous solution of elemental bromine. Now, how can the bromine be extracted from this solution? Let's compare it with a stoppered flask of aqueous bromine from our earlier experiment. A considerable amount of the volatile bromine has accumulated in the airspace above the solution because of the low solubility of bromine in water. This suggests that if bubbles of air are forced through the solution, they will carry away the volatile bromine. A source of compressed air is connected to a dispersion tube. The air bubbles sweep the volatile bromine out of solution. However, in order to concentrate the bromine from this dilute gaseous mixture, we'll need more controlled conditions. Let's start with another portion of concentrated seawater in a system designed to handle the gaseous bromine. You'll recall that we must first acidify the seawater. When the solution is chlorinated, elemental bromine is formed. Compressed air is used to blow the bromine out of the solution. If we try to collect the bromine in a beaker of water, we note that very little of the bromine dissolves. As we should have suspected, the solubility of bromine in water is too low to allow us to concentrate it by this method. To find an effective method of concentrating the bromine, let's consider the solubilities of various bromine compounds in water. We note that hydrogen bromide is highly soluble, confirming our earlier experimental observation.